Preparing for a Photonics Engineer interview. You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you explain the difference between silicon photonics and traditional discrete optical systems? Silicon photonics puts waveguides, splitters, modulators, and sometimes detectors onto a chip. Instead of assembling separate lenses, fibers, and bulk components, the big win is scale. CMOS-style fabrication gives compact, repeatable, high-volume devices. The trade-off is that silicon has indirect bandgap behavior, thermal sensitivity, and coupling loss challenges. Discrete optics remain useful for high-power lasers, specialty wavelengths, or quick prototypes. In practice, I'd choose based on volume, performance, packaging risk, and cost. While answering, focus on integration density, CMOS compatibility, passive and active devices, coupling challenges, thermal sensitivity, cost at volume, and why discrete optics can still win in power or specialty performance. Question 2. Walk me through how you would build an optical link budget for a fiber or photonic integrated circuit system. I start with launched optical power and subtract every deterministic loss. Fiber coupling, waveguide propagation, bends, splitters, filters, modulator insertion loss, connectors, and packaging losses. Then I compare received power against detector sensitivity for the required BER and data rate. I always keep margin for temperature drift, process variation, aging, and alignment error. A good link budget is not just arithmetic. It is a risk model that tells me where measurement, redundancy, or redesign is needed. Make sure to cover transmitter power, coupling loss, propagation loss, splitter loss, modulator insertion loss, receiver sensitivity, noise margin, connector aging, and how you validate assumptions experimentally. Question 3. How do you design a single-mode optical waveguide, and what trade-offs do you consider? Single-mode design means selecting geometry and index contrast, so only the fundamental mode is supported at the operating wavelength. I usually start with effective index or eigenmode simulations, then check confinement, bend loss, group index, and polarization splitting. High confinement enables tight bends, but increases scattering from sidewall roughness and sensitivity to fabrication errors. Lower confinement is more forgiving but larger. The final design depends on footprint, loss target, bandwidth, and manufacturability. In your answer, talk about core and cladding indices, waveguide dimensions, V-number or effective index, confinement, bend radius, dispersion, sidewall roughness, polarization behavior, and fabrication tolerances. Question 4. What are the main sources of optical loss in a photonic chip, and how would you measure and reduce them? Loss usually comes from fiber-to-chip coupling, sidewall scattering, material absorption, bend radiation, mode mismatch, and imperfect splitters or crossings. I measure propagation loss with cutback structures, resonator Q, or spirals, while de-embedding grating or edge coupler losses using calibration structures. To reduce loss, I improve lithography bias, sidewall smoothness, bend radius, mode converters, and material quality. The key is separating packaging loss from on-chip loss, otherwise, you optimize the wrong part of the system. Be sure to mention coupling, propagation, bend, scattering, absorption, mode mismatch, test structures like cutback and ring resonators, calibration strategy, and process or layout improvements that reduce loss. Question 5. Explain how a semiconductor laser works and which parameters you would monitor in qualification. A semiconductor laser converts injected carriers into coherent photons through stimulated emission inside a resonant cavity. Once gain exceeds cavity and material losses, the device reaches threshold and lasers. For qualification, I track threshold current, output power, slope efficiency, wavelength drift, line width, RIN, side mode suppression, and temperature dependence. I also care about burn-in, ESD sensitivity, facet degradation, and packaging stress. A laser can meet power specs initially and still fail if thermal management or reliability is weak. While answering, cover stimulated emission, gain medium, optical cavity, threshold current, slope efficiency, line width, relative intensity noise, wavelength stability, temperature control, lifetime testing, and failure mechanisms. Question 6. What photodetector metrics matter most for a high-speed optical receiver? For a high-speed receiver, I look at responsivity, bandwidth, dark current, capacitance, noise, linearity, and saturation power together. High responsivity helps sensitivity, but large area increases capacitance and reduces bandwidth. Low dark current improves noise floor, especially at low optical power. The detector also needs good impedance and capacitance matching to the TIA. I avoid optimizing the photodiode alone. Receiver performance is set by the detector, amplifier, packaging parasitics, and required BER. Make sure to cover responsivity, quantum efficiency, bandwidth, dark current, capacitance, noise equivalent power, saturation power, linearity, transit time, avalanche gain if relevant, and matching to the transimpedance amplifier. Question 7. How does a Mach-Zehnder modulator work, and what limits its performance? A Mach-Zehnder modulator splits light into two arms, changes the relative phase electrically, then recombines the arms to convert phase shift into intensity modulation. In push-pull operation, one arm advances while the other retards, improving efficiency and reducing chirp. Key limits are V-pi, optical insertion loss, extinction ratio, RF bandwidth, electrode loss, impedance mismatch, and velocity mismatch. Bias drift is also real, so practical systems often need thermal tuning or closed-loop bias control. In your answer, discuss interferometric phase modulation, push-pull drive, V-pi, insertion loss, extinction ratio, chirp, bandwidth, electrode design, impedance matching, velocity matching, and thermal bias control. Question 8. Compare grating couplers and edge couplers for fiber-to-chip coupling. Grating couplers are attractive because they support wafer-level testing and relaxed vertical fiber placement, but they often have narrower bandwidth, polarization sensitivity, and higher loss. Edge couplers can achieve lower loss and broader bandwidth, especially with mode converters, but they need polished facets, tighter alignment, and more complex packaging. For early wafer screening, gratings are convenient. For production transceivers where every dB matters, edge coupling is often worth the packaging effort. Be sure to cover coupling efficiency, bandwidth, polarization sensitivity, wafer level testing, alignment tolerance, fabrication complexity, packaging implications, back reflection, and when each option is preferred in production. Question 9. Which simulation methods would you use for photonic device design? And how do you know when to trust the results? I pick the simulator based on the physics. Eigenmode solvers are great for waveguide modes, FDTD for broadband scattering and resonant behavior, EME for tapers and mode conversion, and FEN for multiphysics or RF electro-optic coupling. I trust results only after checking mesh convergence, boundary conditions, material dispersion, and sensitivity to geometry. Then I compare against measured test structures. Simulation is a design accelerator, not truth. Calibrated models are what make it predictive. While answering, include eigenmode solvers, FDTD, FEM, BPM, EME, compact models, mesh convergence, boundary conditions, material models, calibration with test structures, and limitations of simulation assumptions. Question 10. How would you handle polarization dependence in an optical component or photonic circuit? Polarization dependence appears when TE and TM modes see different effective indices, losses, or coupling efficiencies. I first quantify PDL and wavelength shift using polarization resolved measurements. Then I choose the fix, design for one controlled polarization, use polarization splitters and rotators, make the waveguide more symmetric, or add diversity at the system level. In many silicon photonics products, the practical answer is not eliminating polarization sensitivity, it is managing it with architecture and packaging. Make sure to discuss TE and TM modes, birefringence, polarization-dependent loss, polarization-dependent wavelength shift, rotators, splitters, symmetric waveguide design, measurement approach, and system-level tolerance. Question 11. What thermal effects are important in photonic devices, and how would you mitigate them? Thermal changes shift refractive index, so rings, interferometers, filters, and lasers can drift significantly with temperature. I mitigate this with good heat sinking, layout spacing, thermal isolation where needed, integrated heaters, sensors, and feedback loops. For resonant devices, I budget heater power and tuning range early, not after tape-out. Thermal crosstalk is especially dangerous in dense PICs because tuning one element can detune another. Stability comes from co-designing optics, electronics, package, and control software. In your answer, talk about thermal optic coefficient, resonance drift, phase bias drift, laser wavelength shift, thermal crosstalk, heaters, temperature sensors, control loops, heat sinking, and power performance trade-offs. Question 12. How do you characterize a high-speed optical modulator or receiver in the lab? I start by calibrating the RF path, optical power, probes, and bias supplies. For a modulator, I measure insertion loss, extinction ratio, V-pi, electro-optic S21, I diagrams, and BER under realistic drive conditions. For a receiver, I measure responsivity, bandwidth, noise, overload, sensitivity, and BER. De-embedding cables, probes, and fixtures is critical at high frequency. I also automate sweeps over temperature, wavelength, and bias, because single-point measurements hide real product behavior. Be sure to mention S parameters, I diagrams, BER testing, optical spectrum, extinction ratio, insertion loss, bandwidth, calibration, probe and cable de-embedding, bias conditions, and repeatable test automation. Question 13. A fabricated photonic device performs worse than simulation. How would you debug the discrepancy? I would avoid guessing and break the problem into measurement error, fabrication shift, model error, and packaging impact. First, I verify calibration and de-embed couplers. Then I compare test structures against layout intent, waveguide width, etch depth, sidewall roughness, layer thickness, and material index. If possible, I rerun simulations using measured dimensions from SEM or profilometry. The best debug flow uses simple structures before complex circuits because they reveal which assumption failed. While answering, focus on separating design, fabrication, measurement, and packaging causes using SEM or profilometry data, checking material indices, de-embedding losses, and building a structured root cause plan. Question 14. What are the biggest challenges in packaging a photonic integrated circuit? Packaging often dominates PIC performance and cost. The hard parts are submicron fiber alignment, stable attached materials, low-loss optical interfaces, thermal control, RF routing, mechanical stress, and repeatable assembly. A beautiful chip can fail if the package adds parasitic capacitance, shifts polarization, or drifts with humidity and temperature cycling. I design packaging constraints into the PIC early: alignment marks, spot size converters, keep-outs, heater access, and test structures. Photonics is rarely just a chip problem. Make sure to cover fiber alignment, optical adhesive stability, thermal management, RF interconnect parasitics, electrical probing, hermeticity, mechanical stress, testability, assembly yield, and long-term reliability. Question 15. When do nonlinear optical effects become important, and how can they help or hurt a design? Nonlinear effects matter when optical intensity is high enough that the material response is no longer proportional to the field. They can be useful for wavelength conversion, frequency combs, switching, and supercontinuum generation. They can also hurt through two-photon absorption, free carrier absorption, self-phase modulation, and crosstalk. In silicon, high confinement makes nonlinearities easy to trigger, but losses can limit efficiency. I manage them through power budgeting, dispersion design, material choice, and waveguide geometry. In your answer, discuss Kerr effect, two-photon absorption, free carrier absorption, Raman or Brillouin scattering, four-wave mixing, power density, material choice, dispersion engineering, and signal integrity implications. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.